Electrical Engineering from the Middle East Technical University in Ankara, Turkey, and his MS and PhD degrees in electric power engineering from Rensselaer Polytechnic Institute in Troy, New York. His master's and doctoral work focused on power electronics and the development of control algorithms for electric machines. He's currently a professor of electrical and computer engineering at the University of Akron, engaged in teaching and research. And prior to joining UA, he worked for 9 years in industry, developing power converters and electric drives for automotive and industrial markets. He has been leading a number of research programs supported by the National Science Foundation, the U.S. Army, U.S. Academy Transit Research Board, Department of Energy, ABB, GE Global Research, PowerAmerica, Bendix, CVS, State of Ohio, and others. He's very active in IEEE activities, and he's the chair of the IEEE IAS Renewable and Sustainable Energy Conversion Systems Committee. And with that, I'd welcome Dr. Sozer. Yilmaz, are you there? Yilmaz, I see you're still logged in, but I can't hear you. Yilmaz, are you having trouble with the audio? Give me a minute. Let me shoot him a quick email. We appear to be having some technical difficulties, so please give me a minute to see if we can resolve these problems. Yilmaz, I see your screen.
Hello. Can you hear me?
Yes,
okay.
I can hear you.
All right. Yeah, sorry, I had to log in again.
Okay, we're ready.
Okay. Okay. Hi, everyone. Thank you for joining for the webinar. My talk today will be on high bandwidth silicon carbide inverters for motor drive applications. Let me start with first the introduction. I provide motivation for the more efficient electric machine drives and then opportunities. Then I'll provide the capabilities of the wide bandgap devices and opportunities for the electric machine drives applications. So specifically, the detailed design for the high bandwidth single phase inverter that we have both simulation and experimental verification, and I will go through the design process and specifically the control algorithm development, the hardware design, and also through that the work will be extended for the switch reluctance motor drive with the silicon carbide devices. So I provide the motivation to use better power devices to enable the better control to improve the performance of the switch reluctance machines. So let me start with the introduction. So as you know, the energy efficiency in electric machine drives are very important. There are government mandates to increase the efficiency of the electric machine drives in household applications, industrial applications in near future, and also for the electric vehicle and the traction market. The requirements itself is very tough to meet. Like the efficiency should be very high, especially for the electric vehicles, since the main motivation to increase the energy conversion efficiency. So any bit of increase in the efficiency of the motors or the inverters will be appreciated and required. In addition to the efficiency, the packaging, the size, and the environment and conditions are very tough especially for the electric vehicles. So those improvements in the electric machine drives, part of it would come from through the electric motor design. So either through the new materials, new core materials, or new magnet materials would help in improving the performance of the electric machines. The other approach will be the new machine topologies. We have almost conventional, like a current magnet induction machine. In addition to that, now the new topologies for the axial flux machine, transverse flux machines are important in increasing the efficiency and reducing the size and cost. And in parallel, so to have a better design, the better loss estimation for the design optimizations are also important. Estimating the core loss of the electric machine is very challenging, and then any improvements in that would help to get a better machines. So that's on the machine design, and another help would come from the improvements through the power converters. That would come with the new power devices, that especially with the wide bandgap devices, that would help on the efficiency, and also with the higher efficiencies, the cooling methods, cooling requirements would be enhanced, and similarly for the packaging. So the new devices would also help to package the inverter, power inverters for the motor drives better, so that the performance of the overall system can be enhanced. And in parallel, another improvement would come from the better control algorithms. For example, the direct torque control, I provide the plot that with the higher bandwidth controllers, the torque ripple can be reduced significantly. That's in some applications the torque ripple may not be a problem, but some applications like servo applications and the power steering electric machine applications, the torque ripple might be quite important, and it could be challenging, and it cannot be enhanced without a better control algorithms. Similarly, the flux control, it's more direct approach. So if it can be achieved in the electric machines, the torque speed range of the electric machines can be controlled in a much better way that will help the machine performance. The acoustic noise is also important. Once the machine is designed, or even in the design process, the machine can be enhanced further so that we have a less acoustic noise, or through the control, through the better control, the acoustic noise of the machine can be also enhanced. So the control algorithms, the algorithms itself can be improved, but the better algorithms is also needed. They also require to have a better hardware design, which could have a higher bandwidth so that the new algorithms can be implemented, especially for the controllers requiring a high bandwidth applications. So let's look at let me summarize the capabilities of the wide bandgap devices that I see that could fit on the motor drives. Then we can go to the opportunities, look at opportunities for the electric machines. So the wide bandgap devices, especially silicon carbides, they have higher breakdown voltage. It's reported that 10 times the dielectric breakdown field strength of the silicon devices. So that will help these devices can handle higher voltages. Another important factor for the wide bandgap devices, the silicon carbide devices, are the higher junction temperature operation. That will help to reduce the heatsink requirements and then to get a better thermal management for the power converter. Similarly, also thermal conductivity is 3 times for the silicon devices. So again, that requires a less heat sink or less thermal management efforts. All the smaller size, the devices itself are smaller. It will help for the higher power density, and also the better thermal performance will also help to get a higher density motor drive. So in addition to that, of course, it's very important the lower turn-on losses and also the lower switching losses will help to reduce the losses and then increase the efficiency. In addition, the long short circuit withstand rating, it will help to release the requirements on the protection circuits, and then will provide a more reliable circuit operation. So I just provided in this slide the comparison of the switching actions for the silicon carbide and the silicon devices. It's clearly seen that the turn-off time is significantly less for the silicon carbide devices, and then the desired operating frequencies for the silicon carbide devices are much higher compared to the silicon. So from there, definitely the higher switching frequencies can be achieved through the silicon carbide devices for the high power applications. That will help to have a smaller magnetics, especially the capacitors and inductors in the electric machine drives. So let's look at the opportunities for the electric machine drive applications. So I'll provide like a sample design for one machine drive application. So we looked at the preliminary design and then compared the requirements for the capacitance, the requirements for the efficiency, performance, and then requirements for the devices. So in this application, it's a high-speed double stator permanent magnet synchronous machine drive for hybrid vehicles. It's definitely, since it's for the vehicle applications, there are packaging constraints that the overall drive should fit into a specified space. That's very challenging to meet. And it's high-speed operations. Efficiency is definitely important. Is a wide-speed operations, so that through the machine design also for the high-speed operations. So for the new approach is to go to the higher number of poles. That will increase the fundamental frequency, and then since it's operating at the higher speeds, that's also another factor to go to the higher fundamental speed, higher fundamental frequency. And with that, definitely to produce good current waveforms at higher speeds, higher fundamental frequency, it requires higher switching frequencies. Thermal management is also a challenge, since it's electric vehicles. The drive goes under hood. It's a harsh environment, and then temperature is quite high. The environment temperature is quite high. So for this application, the total phase current of the motor from the machine design is 185 amp. That's shared between the two inverters. This design is the double stator, has a two-stator to produce the required torque over a speed range. and then the DC bus voltage is selected as a 600 volt. So given that phase current rating, the individual inverter phase current rating will be half of that. It's 92.5 amp. So let's look at the capacitor sizing. So without considering without thinking about which power devices will be used, just comparing the switching frequency of 20 kilohertz and 100 kilohertz, the required capacitor, since this is the switching frequency on the phase currents, it will be reflected on the ripple on the DC bus current, which should be filtered by the capacitors before getting into the main phase, the main DC bus current after main DC bus current from the battery. So that if you compare these two frequencies, the capacitor can be reduced significantly. And for the higher switching frequency, we selected two sets of capacitors. One set is to achieve a 453 microfarad, the other one is a 91 microfarad. The definitely price is different, and then also the volume of the capacitors for these two comparison is reduced significantly. So the other analysis will be the loss comparison to meet 92.5 amp in the phase currents. So we have selected silicon carbide and then the IGBT, another silicon carbide and the IGBT to compare. So the current ratings are similar. So yeah, both of them are MOSFET, the Axis MOSFET and the silicon carbide MOSFET. So the turn on and then turn off switching energies are quite different when we compare these two devices, and also the thermal performance were different. So we calculated the power loss for these two inverters. One is a silicon carbide, one with the normal MOSFET. So when we compare that at the 20 kilohertz, the silicon carbide power loss is lower than the power MOSFET, and then the difference is more prominent when we do the comparison at the 100 kilohertz. And then the junction temperature requirements for the same cooling is also better for the silicon carbide MOSFET. So that basically shows that there is an opportunity to use wide bandgap devices in the electric machine drive applications. Although the cost of the silicon carbide devices are high, the thermal management is easier, efficiency is higher, and also the capacitor requirements are low. The sum of the increase in the price due to the wide bandgap devices can be compensated by reduction in the passive elements. So this was more like a preliminary analysis for the permanent magnet synchronous machine for the vehicle applications. I will show you more detailed analysis, both the control and the hardware development for the single-phase inverter. Although the application is on the electric machines, it's more like developing a unit that could generate a desired flux in specified cores. This unit is developed to have is like a big signal generator that could generate any flux that's desired in a specified core. This is very important to predict the core losses in the electric machines. So as you see in the block diagram, the signal, the system is developed and filtered so that the filtered signal is applied to the specified cores, and through the control, the output is generated. So the filter was necessary. The testing is mostly required the saturating core, so it's quite nonlinear load, and the various voltage control structures are available in the literature, but we looked at that, and then I will provide you some examples for the control to produce a flux in the core. So this application is important as it quite mimics the flux control in the electric machines. So this is the flux control in a specified core. So it's a single phase inverter. So I will show you the control algorithms first. Then we'll go through the design process, and then I'll show you the need to use a very high bandwidth controller, and also need to use the power devices that can switch at very high frequencies at the desired power level. Let me go a little bit more on the application. So as I mentioned at the beginning of my presentation, the prediction of the core losses is very important in the electric machines. So when we design in the design of the electric machines, the flux in the various parts of the electric machines are quite different. They might have a DC biasing. At some regions, they might have the very high frequency component, very high frequency flux at some truth areas, and then the different waveforms in the different region of the electric machines. So it's not very accurate to assume a core material and then assume a frequency of operation, then predict the losses based on that. So and then we see that most of the time it's like the prediction and the actual experimentation changes almost 50% from the actual values. So this approach is to more like knowing the fluxes appear in the electric machine of different regions, and then experimentally generate that flux in the core, in the specified core, and then measuring the core losses through this equipment. So this slide shows the process. The first is to do the finite element analysis, and then mapping the loss regions and determining the flux density waveforms, and the analysis of the core losses under actual flux density waveforms. So applying those required flux densities in the core, and then determining the loss per volume mass for each region, and then estimating the total core loss. So that's the application, but the area that I'm going to focus more on, developing this converter. So it's a single phase inverter, so we apply a DC voltage and then generate a AC flux in the core. So as I mentioned, this quite mimics the flux control in the electric machine. So you can see the waveforms in different region of the power converter. As I said, it's a single phase inverter. The filtering elements that's applying a voltage to the core in the primary that will generate a flux in the core, and then the secondary coils are used to measure the flux in the core. So if you go through and like open loop control, if you generate a voltage that is applied and then applied at the output of the inverter. So since the load is quite nonlinear, that will distort the voltage across the capacitor, and that's the second graph from the left. And then third graph from the left will show you the current that goes into the core windings, and the last graph in the second row will show you the flux waveform, that the voltage waveform that's related to the flux. As you see, with this chain, with this control, open loop control, the flux is quite distorted. So the second approach will be the voltage control. It basically directly controlling the voltage across the capacitor with the closed loop control. So if you just concentrate on the voltage, on the capacitor voltage, you see the current on the third from the left is quite distorted because the core is nonlinear. Then the voltage, the flux that we measure is also quite distorted. So then what we developed is the flux control. So we directly measure the voltage on the windings and then determine the flux in the core and then directly control that flux, which could produce a distorted voltage on the capacitor, the distorted current waveform, but eventually the voltage that we measure at the secondary terminals is quite sinusoidal. That's actually what we want. We could also want more, as we determined through the finite element analysis, is more high frequency flux, so that we should be able to also generate that. So what's the challenge here? It's basically the flux that we wanted to generate is very high frequency. It could have a DC bias. It could have different fundamental frequencies. On top of it, also different frequencies as the flux in the electric machines are, the frequency of the flux at the electric machines in different regions could be quite different. So the control algorithm that we proposed is a one branch that's responsible for the DC flux control to have a bias. So if you look at the block diagram, which is the control block diagram, so this portion will be the DC flux controller. So that will command a DC reference flux, and eventually it's generated a DC reference current through the feedback compensator. The voltage will be generated to generate a DC offset. The second part of the controller here has a three control loops. It will generate an AC flux that's commanded to generate in the core. Is a feed forward terms. There's a feedback part, and then there's a periodic controller. So periodic controller will help over different cycles. It basically tune itself to generate AC flux, and then feedback compensator will the main part of the controller to regulate the flux in the core by updating the voltage command from the inverter. So addition of this, all controllers will generate the desired flux in the core. So before we implement the control, we should have a system model. So the model will have an inverter part, which has the supply voltage and an LC filter. The transformer is a toroidal transformer. It has a leakage inductance, magnetizing inductance. The secondary is also have a leakage inductance. To ease the modeling and then to make it linear, so we combine the leakage and the magnetizing inductance. As we don't have the load on the secondary, so we can also neglect the leakage on the secondary. So with this circuitry, the state space model it is developed, and then we have a three states, which is the inductor current, the current that goes into toroid, the capacitor voltage, and the secondary voltage, which is that we can measure at the secondary of the transformer. So it's a linear model, it's a state space model. It relates the input and output, and the parameters are based on the capacitor, resistance, inductance, and the number of turns, and magnetizing and the leakage inductance of the core. So based on that model, the three control part the key controller here is the optimal state feedback control design, where the controllers KP21, KP2, KP23, it's produced based on the state matrix, the optimal control design, and J is here is the cost function, and from the Riccati equations we will be able to get we will be able to determine the K values through this the matrix multiplications. So the J itself is the cost function, and then the matrices that we enter will specify the performance of the controller. And similarly, this controller is also used for the other controller is the PI controller for the DC offset generations, and we have the repetitive controller that will help to generate the periodic repetitive controller that will help to enhance the performance of the controller over the cycles. So for given parameters, this is the control design. We just basically, based on the model, we implemented the matrix calculations, and then we came up with a control design. And I can show you the performance of the controller, where the flux density is the sense voltage is over a cycle. It improves, the performance is improved. The sense voltage error at the beginning is high. As it goes through, it's very low. It's reduced to a very low values, and you can see that the nonlinear behavior of the voltage that we have on the capacitor, inductor current, and then the input voltage from the inverter. So here is the key, where we have a 100 Hertz sine wave with 0 offset, 400 Hertz trapezoidal voltage with 1.4 Tesla DC offset, and 1000 Hertz fundamental with the third, fifth, seventh harmonic components, the voltage waveform. The controller performance is excellent, but as you see here, the 1000 Hertz is the fundamental, and we have additional harmonics that goes up to 7th harmonics, so that the controller should handle basically 7 kilohertz. And we found that that's only possible if we can increase the switching frequency significantly so that the inverter that we have can generate this flux waveforms. And what we found is the only way that we can achieve this is through the silicon carbide devices, where the operating frequency we achieved with the hardware is 150 kilohertz, 900 volt peak, and 130 amp peak conditions. So for the converter design, we had to use a laminated DC bus with distributed capacitors. That was important to as the switching frequency are 150 kilohertz, that it's required to have a laminated DC bus. We have used a high bandwidth, the high performance TI DSP, and then toroidal transformer as a load. So in the hardware development, definitely the requirement went up to 10 kilohertz. So for the fundamental frequency, the switching frequency to achieve a THC of 3%, we have to use a 150 kilohertz switching frequency, and the phase current is 100 amp, the phase voltage is 600 volt, to be able to generate that much flux waveform, desired flux waveforms in the core. We have achieved this by just using a two MOSFET modules, silicon carbide MOSFET modules placed in the heatsink, as we see it in the block diagram. That's the board design. So the parasitic inductance, especially for that high frequency between the DC bus capacitors and the MOSFET modules, needs to be minimized to reduce the ringing effects and the excessive overshoots. So it's desired to reduce the field due to the bus currents. So we found that the two approach to cancel the field that's produced by the current movement is either using a parallel plate or the coplanar plate for the windings for the currents on the bus. So we can see that the fields canceling each other with the parallel or the coplanar plate overlapping, and then it's clearly seen that the parallel plate is a better approach. And we also found it in the literature that inductance per unit length for the coplanar arrangement is almost 6 times higher than the parallel plate arrangement, so that the parallel plate arrangement was a choice for us for the circuit board design. So distributed low equivalent series ESL capacitors are connected through the PCB between the DC supply and the switches. And in addition, the variety of capacitors of different capacitance range have been placed close to the MOSFET modules for further elimination of the parasitic inductance, ringing, and overshoots. So we kind of predicted the parasitic inductance as 14 nanohenry. Here's the board design. We basically starting with the high value capacitors. As we get close to the MOSFETs, we started from the 1200 microfarad capacitors connected in parallel, and then we go to the 50 microfarad capacitors and 1.2, and the smaller capacitors as we go get close to the MOSFETs to reduce the ringing as much as possible. And with experimental results, like we have seen in the simulations, different 250 hertz sine wave with the zero offset at the left figure is perfectly produced. 80 hertz stator flux of an induction IPMSM is also generated, is very close to the reference flux, and then 480 hertz rotor flux with the higher harmonics on it is also generated with the device that we have developed. I think so far that's what the things that I covered is the implementation of the silicon carbide devices in the inverter to generate a flux that could be found in the electric machines. And then definitely there was a need for the wide bandgap devices, the silicon carbide devices, to achieve that much power level at that frequency and then have a very good high bandwidth controller. So then the extension of this approach is the opportunities for using the wide bandgap devices in the electric machine drives. So in the one application could be that we are working on a project right now on developing a switch reluctance machine-based motor drive for the hybrid trucks. So the main reason for the selection of the switch reluctance machine is the reliability, and it doesn't require permanent magnets. That is a big plus in the case of the failures. The shutdown of the machine is much easier compared to the other machines. That was the main reason to choose a switch reluctance machine. Besides the it doesn't require a permanent the rare earth materials. That was also a big plus to selecting this type of machine for the hybrid trucks applications. So it provides a more reliable and a low cost. The challenge for the switch reluctance machine is the torque ripple and the acoustic noise. So the one approach, as I mentioned, is through the design to develop a design so that the torque ripple could be lower, acoustic noise could be lower. The second thing can be approach is through the control. Definitely going towards the higher number of poles in the stator and the rotor would help reducing the acoustic noise significantly. So the deformation on the stator through the radial force, as we increase the number of poles, will reduce the pulsations, the frequency of the pulsation, and it will reduce the deflection, and it will reduce the acoustic noise. But as we go, especially for the vehicle application, as we go to the higher speeds, using a higher number of poles will impact on the too much on the increase the fundamental frequency significantly. That will require, so if we are regulating the current at that high frequency with this higher number of poles, it will require a very high bandwidth controller. And if we are also trying to reduce the torque ripple and acoustic noise through the control, that will require additional control algorithms. To implement those control algorithms also definitely requires a much higher switching frequency. And then the silicon carbide devices would be a good choice in these applications to increase the efficiency and also to enable to implement those control algorithms. One control algorithm is to shape the current waveform to reduce the torque ripple. Is based on the position, the current waveform can be shaped rather than just pulsing the currents, like turning on and regulating at the desired the current levels. If we can shape the current waveform during the turn-on period, as we see it on the figure at the left corner, if you can shape it during the turn-on and even during the conduction period, and then continue to regulate the current during the turn-off period, it will help a lot in reducing the torque. So that's one result that we could see on the torque production and the current waveform. As you see the current waveform, it's not only regulated at a constant level, it shapes during the turn-on period, and also during the turn-off period, the current is also controlled. So the resultant torque waveform is quite smooth, that the ripple is almost is cancelled through the better control on the torque on the current waveform. So that's for the current shaping to reduce the torque ripple. Another application is the acoustic noise reduction with the current shaping. The acoustic noise is basically happens in the switch reluctance machine when the rotor poles is getting close to the stator poles. The force applied on the stator poles, it will provide a deflection. So that will cause a vibration on the stator, deformation on the stator, and then it will cause acoustic noise on the stator. So then, if we can, rather than pulse currents, if we can apply a current waveform that has additional harmonics on it, so individual radial forces can be shaped, and then when we add the phase forces, so that the force ripple can be reduced significantly, so that so we can compare these two waveforms. One is a standard excitation where the force ripple at the addition of the three phases the force has a significant ripple, and then if we shape the currents, the force is ripple is significantly reduced, and then that's the main cause for the acoustic noise. So the project that we're currently working on and DC, what we are looking at the DC bus capacitors is, so in addition to the ripple, the high switching frequency ripple, there is during the commutation, what we have is the commutation ripple will enforce a ripple on the DC bus current. So that's significant. So the control algorithms that will shape the currents will also help to reduce this DC bus ripple current. It will improve the performance will reduce the torque ripple, and it will also reduce the ripple on the DC bus current, which could reduce the requirement for the DC bus capacitors. So I just wanted to give you some applications in the electric machine drives that could use the silicon carbide or the wide bandgap devices to improve the performance, to conclude my presentations. So I guess at this point I will be happy to get your questions.
Thank you very much, Dr. Sozer. That was a very interesting presentation. Good to see the new approaches for trying to reduce the torque ripple on these switched reluctance motors. Are there any questions? We have a few minutes, and there are a reasonable number of people online, so I don't think we need to use the chat window. So if you want to speak your question orally, we have about 10 minutes.
Sure. Hi, this is Eric Person from Infineon. I have a question for you. So the previous example where you were showing the filtered, voltage source inverter essentially, and then looking at this SR drive, have you also considered filtering the SR drive? Would there be any benefit in terms of maybe reducing the ripple current or reducing the DVDT, winding problems and so on in the SR approach?
Yeah, this is a very good question. Definitely we need some filter to reduce the DVDT on the SR drive. It leads to the silicon. I mean, we go to the silicon carbide devices. The DVDT is high. To reduce the impact on the windings, we could have some filter to reduce that. But if we filter beyond that, so we will get a delay in the power that we applied. It could impact the torque performance, and also the filter is kind of additional losses in the system.
Yeah.
So yeah, as you said, there should be a kind of balance, like how much filter we want, and then what type of frequency that we should target, or how much reduction we should have in the DVDT.
Okay. Maybe a follow-on, if I could, similar line of questioning, I guess, just in general for voltage source inverters, with IGBTs, the DVDT has been limited to maybe 5 or 10 volt per nanosecond, something like that, usually intentionally because of winding partial discharge and potential corona and so on. So are you seeing any trend in the industry or, with wide bandgap devices able to deliver, 50 or even 100 volt per nanosecond? Is the approach, in your view, going to be more to filter the edges and suffer that loss, as you mentioned, or can the machines be designed to accommodate that high of a DVDT?
In terms of the current, machine is itself an inductor. So for the current waveform, it's definitely it's going to be filtered. The other approach in the machine design is to go through more elaborate design in the insulations of the checking the insulation of the windings, the potting material, even in the bearing selections or so. It's definitely an option, but I don't. It's not in the applications yet, but those are the approaches that could be taken.
Okay, thank you.
Mm-hmm.
Are there any other questions?
Looks like everyone's muted, so if you are trying to ask a question, click your unmute.
I'm sorry. Okay. I just unmuted everyone.
Oh, okay. Okay, can you hear me now?
Yep.
Okay, hi. This is John Wenxiao from Wolfspeed. Question regarding the switch reluctant motor. What kind of applications, like any company are using SR motor for EV or for other higher power applications?
The one that we are doing is a new design for hybrid truck applications. So that's we did that detailed comparison. Basically designed the possible machine type, use the all like a possible configurations. We checked the axial flux machine, interior permanent magnet machine, and induction machine, and the switch reluctance machine.
I think he was asking if there are any existing commercial applications where switch reluctance machines are used.
Right.
There are some that I kind of see it. So I'm not sure what the volumes are for those products.
Can you say what industry they're in?
It's for the mining industry. That there are a couple SR drives, and I think Nidec also has some lines for the SR machines.
Okay.
Thank you.
Are there more questions?
Hi, this is Eric again. I had a question, or I'm sorry, a comment for Professor Sozer. Could you go back to the slide where you compared the silicon carbide device with the IXYS MOSFET losses? Towards the beginning. Yeah, here. I think you may find that silicon carbide is even better. I'm not sure this is, are you including the reverse recovery loss of the IXYS? Or, it doesn't matter the brand. Any 850 volt MOSFET has really large and long QRR. I don't know that you'll be able to get switching in less than 300-400 nanoseconds, because just the reverse recovery of a part like this is 200 or 300 nanoseconds. So if you include the reverse recovery loss of the silicon FET here, I think you'll get an even more dramatic comparison between silicon versus silicon carbide.
Yes. Yeah, you are right. This was a preliminary comparison, and there was enough power difference that we've seen.
Yeah. Okay, the conclusion would still be the same, but yeah. Okay. That was all. Thank you.
Thank you.
Are there more questions? Going once? Going twice? Okay, well, thank you very much, Dr. Sozer. That was a very good presentation, and thank you all for joining us today at PowerAmerica. And we'll see you again, hopefully, on Wednesday, January 10th. Have a great day.
Thank you. Bye-bye.
You'll get a recording sent to you automatically through WebEx, and if you shoot me an email, I can send you a copy of the file. I just don't want to blast it out to everyone.
All right. Very good. Thank you.
You're welcome.